Imagine a particle traveling through space with so much energy that it makes the most powerful events on Earth look like tiny sparks. It moves at nearly the speed of light, carrying more force than anything we can create in our most advanced laboratories. These are ultra-high energy cosmic rays, and they are some of the most mysterious messengers the universe has ever sent our way. For decades, scientists have been utterly baffled by their existence because, according to everything we know about physics, these particles simply should not be able to reach us. Yet here they are, defying explanation and challenging our understanding of the cosmos itself. What makes these cosmic rays so extraordinary isn't just their unbelievable energy, it's the profound mystery behind their origins. Think about it, something out there, somewhere in the vast expanse of space, is accelerating particles to energies that dwarf anything we can produce on Earth. The Large Hadron Collider, our most powerful particle accelerator, is like a toy compared to whatever cosmic engine is firing these rays across the universe. And the strangest part, we still don't know what that engine is. These rays arrive at Earth from directions that point to nothing, empty space, void. It's as if the universe is playing the ultimate game of hide and seek with us, and we're only just beginning to grasp the rules. In this video, we're embarking on a journey to explore 30 of the most mind-bending ultra-high energy cosmic ray events ever detected, each one a puzzle that defies our current understanding of physics. From particles that appear to break the laws of the universe to detections that leave even the most seasoned researchers speechless, we're diving deep into the enigmas that continue to captivate and confuse the scientific community. This isn't just a story about particles, it's a story about human curiosity, our relentless drive to understand the unknown, and the awe-inspiring realization that the universe still holds secrets beyond our wildest imagination. So settle in, because what you're about to discover might just change how you see the cosmos forever. Our journey into the unexplained begins with perhaps the most famous cosmic ray ever recorded, an event so astonishing it earned the nickname every scientist wishes they could give a discovery. It was October 15, 1991. High above the Dugway Proving Ground in Utah, a single subatomic particle, likely a proton, slammed into the upper atmosphere. It wasn't just any particle. This one was moving with such incomprehensible speed and energy that when scientists first calculated the numbers, their reaction was one of pure, stunned disbelief. They had just witnessed the "oh my God" particle. To understand why this event caused such a shock, we need to talk about scale. The energy of cosmic rays is measured in electron volts. A typical particle from the Sun might have an energy of a few million electron volts. The protons circulating in the Large Hadron Collider, the most powerful machine ever built by humanity, reach energies of about 6.5 trillion electron volts. The "oh my God" particle, it was carrying a staggering 320 exelectron volts. That's 320 followed by 18 zeros. This single subatomic particle had the kinetic energy of a well-thrown baseball, all compressed into a tiny speck smaller than an atom. It was traveling at 99.9999999999995% of the speed of light. At that velocity, if you were racing a light beam across our galaxy, you would lose by less than a single inch. The existence of such a particle shatters our models of physics. Think of space as a cosmic highway. A proton traveling through it isn't alone. It's constantly bumping into the faint glow of light left over from the Big Bang, what we call the cosmic microwave background. It's like driving through a gentle, universe-wide mist. For a proton with the energy of the "oh my God" particle, this mist should act like thick molasses. Over a long journey, these countless tiny collisions should rob the particle of its energy, slowing it down long before it could ever reach Earth. According to our best theories, this particle shouldn't exist. It shouldn't have been able to get here, and yet it did. This leaves us with a monumental puzzle. What cosmic event could possibly act as a particle accelerator on such an unimaginable scale? It would require forces billions of times more powerful than a supernova. Potential suspects like active galactic nuclei with their supermassive black holes or incredibly rare gamma-ray bursts are still theoretical candidates. None provide a perfect, satisfying answer. The oh my god particle is a ghost, a messenger from an event of cataclysmic power that arrived without a return address, challenging us to figure out just what in the universe is capable of such an incredible feat. Just when scientists thought the oh my god particle was a once-in-a-lifetime anomaly, the universe sent another message, this one so powerful it was named after a goddess. In May 2021, the Telescope Array project in Utah, the same type of facility that detected the legendary oh my god event, recorded something extraordinary. A cosmic ray struck the atmosphere with an energy of approximately 240 exaelectron volts. In a tradition of giving these bewildering events memorable names, the international team of researchers called it the Amaterasu particle, after the Japanese sun goddess who is said to have illuminated the world. The energy itself is staggering, placing it firmly in the same league as its infamous predecessor. But the true mystery of Amaterasu isn't just its raw power, it's the bewildering emptiness from which it came. When researchers traced the particle's path backwards, trying to find its point of origin in the cosmos, the trail led them to a region of space known as the local void. This is not a place of brilliant galaxies or swirling nebulae. It is, as the name suggests, a void. A vast, seemingly empty expanse of nothingness bordering our own Milky Way galaxy. It is one of the least dense areas in our entire cosmic neighborhood. Finding the source of such an unimaginably energetic particle, there is like hearing a deafening roar come from a silent, empty room. It simply doesn't make any sense. This deepens the mystery in a profound way. For decades, the leading theory pointed to extremely violent astronomical events as the likely accelerators for these ultra-high-energy particles. We look to the hearts of active galaxies, where supermassive black holes eject colossal jets of matter. We considered the aftermath of colliding galaxies or the explosive deaths of massive stars in supernova. These are places of chaos and tremendous power, logical cosmic factories for such particles. The local void contains none of these things. It is a desert. So the question becomes, if not a cataclysmic event, then what? What natural phenomenon hidden in that void possesses an engine capable of launching a single particle with more energy than we can possibly create on Earth? The Amaterasu particle forces us to confront the limits of our knowledge and perhaps even consider possibilities that sound like they belong in science fiction. Could there be unknown astrophysical objects lurking in these voids, completely invisible to our current telescopes? Might our understanding of particle physics itself be incomplete, suggesting these particles can travel in ways we haven't yet dreamed of? Or does their arrival from nowhere hint at something even more exotic, like defects in the very fabric of space-time? This single detection did more than just add another data point. It amplified the cosmic puzzle, proving that the oh my god particle wasn't a fluke and that the universe holds secrets far stranger than we ever imagined. And just when the scientific community was grappling with the profound mystery of the Amaterasu particle, the cosmos delivered another 1-2 punch that deepened the intrigue. Mere months after Amaterasu's detection, the same observatory recorded another ultra-high-energy cosmic ray, and then another. These weren't just random events, they were twins, a pair of astonishing particles that arrived from the same bewildering place, the depths of another cosmic void. This pair of detections transformed a single anomaly into a pattern, and patterns are what truly force scientists to rethink their models. For the longest time, the prevailing theory was beautifully simple. The most energetic particles in the universe must come from the most energetic places. We look to the brilliant, violent hearts of active galactic nuclei, where supermassive black holes shred matter and accelerate it to incredible speeds in colossal jets. We pointed to the chaotic environments of galaxy clusters or the explosive fury of merging neutron stars. These are the cosmic powerhouses, the logical candidates for such extreme particle acceleration. But these two new particles did not come from a powerhouse. Their trajectories pointed back to a vast, empty region of space, an area with a startling lack of galaxies, star clusters, or any of the usual astrophysical suspects. It's the equivalent of detecting the roar of a jet engine and tracing the sound back to a silent, empty field. Our models of particle physics and astrophysics, which work so well in explaining the chaotic, dense environments of the universe, suddenly have nothing to say about the quiet, empty parts. The very existence of these twin anomalies suggests that our understanding of where these particles can be born is fundamentally incomplete, if not entirely wrong. This contradiction opens up a realm of fascinating and almost unsettling possibilities. One idea is that these voids aren't actually empty. They might be hiding something our telescopes cannot see. Perhaps there are faint, dark galaxies made mostly of mysterious dark matter, and the interactions within them are capable of generating these incredible particles. Or maybe our understanding of magnetic fields in these empty spaces is flawed, and they can act as unseen guides, funneling particles from a distant, powerful event and bending their paths to make it appear they came from nowhere. The most thrilling possibility is that these particles are not being accelerated by a single cataclysmic event at all, but are instead the product of something entirely new. They could be evidence of exotic physics, such as the decay of hypothetical superheavy particles left over from the Big Bang, or even the result of cosmic defects in the fabric of spacetime itself, tiny cracks in the universe releasing immense energy. The twin anomalies from the void don't just ask a question, they challenge the very framework we use to ask questions, reminding us that the greatest discoveries often come from the places we least expect to look. But the mystery of cosmic rays doesn't only lie in the unimaginably powerful outliers. It also lies in the particles that seem to break the rules on a slightly smaller, yet no less baffling scale. Consider three specific detections, each with an energy hovering just below that critical GZK cutoff. This cutoff, named for physicists Greisen, Zatsepin, and Kuzmin, represents a fundamental speed limit for the cosmic highway. It's the point where a proton traveling across the universe should have lost all its energy to collisions with the cosmic microwave background radiation. Particles with energies above this limit, like the Oh My God and Amaterasu particles, are the rule breakers that shouldn't be able to travel far. Particles below it, however, should be the local commuters, cosmic rays that originated from somewhere relatively close within our own galactic neighborhood. This is where the plot thickens. These three cosmic rays had precisely that kind of energy, suggesting they were born right here in the Milky Way. When researchers traced their paths back to find their source, they expected to pinpoint a known celestial powerhouse. Our galaxy is home to several brilliant candidates, the violent remnants of supernova explosions, powerful pulsars spinning at incredible speeds, or the intense environment around the supermassive black hole at our galactic center. Any one of these could, in theory, serve as a natural particle accelerator. Yet, when the backward tracing was complete, the trails of these three particles led to nothing. Empty space, they appeared to originate from within the familiar confines of the Milky Way, but from locations devoid of any known object capable of such acceleration. This creates a paradox that challenges two major pillars of astrophysics at once. First, it questions our models of galactic magnetic confinement. The Milky Way is wrapped in a vast, invisible magnetic field. For a cosmic ray to escape its source and travel across the galaxy to reach us, it must have enough energy to break free from this magnetic grip, much like a rocket needs enough thrust to escape Earth's gravity. These particles had that energy, But if they broke free from a specific source, that source should be visible. The fact that it's not suggests a flaw in our understanding of how these magnetic fields contain and guide energetic particles. Perhaps the fields are stronger, weaker, or shaped differently than our models predict, somehow concealing the true origins. Second, and perhaps more intriguingly, it challenges our very understanding of acceleration mechanisms within the galaxy. We have a short list of known objects that can push particles to these incredible energies. If none of them are at the coordinates these rays came from, then what is? This forces scientists to consider the existence of entirely new classes of astrophysical objects, invisible engines hidden in plain sight within our own galaxy. These could be dark matter clumps interacting in ways we don't understand, or perhaps quiet, dormant remnants of ancient stellar explosions that have faded from view but are still capable of immense particle acceleration. These three galactic escapees are like fingerprints found at a scene with no suspect, evidence of a crime without a criminal, compelling us to acknowledge that even our own cosmic backyard holds profound secrets waiting to be uncovered. Sometimes the universe doesn't just send us a mystery from the void, it sends one from our own cosmic backyard, and that can be even more perplexing. This brings us to a detection that seemed to offer a moment of clarity, only to plunge us into a deeper paradox. It involved our galactic neighbor, Centaurus A. At a mere 13 million light-years away, this peculiar galaxy is one of the closest active galaxies to Earth, and for a long time, it's been a prime suspect in the search for cosmic ray factories. With its gigantic jets of matter erupting from a supermassive black hole, it looks exactly like the kind of violent engine we've been searching for. So, when a high-energy cosmic ray was detected and its path seemed to point right back to Centaurus A, you'd think scientists would have celebrated a solved case. Instead, they were left with a new kind of headache. The problem wasn't the source, it was the sheer force of the delivery. This particular cosmic ray arrived with an energy level that was simply too high, far exceeding what our best models predict a galaxy like Centaurus should be capable of producing. Think of it like this: you hear a loud noise and trace it to your neighbor's workshop. You know they have a powerful tool, maybe the loudest hammer on the block. But when you arrive, you realize the sound you heard was not a hammer, it was a sonic boom. The tool is familiar, but the output is impossibly, disproportionately powerful. That's the Centaurus a misfire. We found the workshop, but we can't explain the product coming out of it. This creates a fascinating and frustrating paradox for astrophysicists. On one hand, Centaurus possesses all the right ingredients. Its central black hole is actively feeding, launching colossal jets of plasma and radiation that stretch for millions of light years into intergalactic space. These jets are natural particle accelerators on a breathtaking scale, and they should, in theory, be able to produce cosmic rays. Our models are built around the physics of these environments, calculating the maximum energy a particle could realistically gain as it gets whipped around by intense magnetic fields and shockwaves within the jet. The detected particle blew right past that calculated maximum. It's as if our understanding of the engine's horsepower is fundamentally off. This misfire forces us to confront a critical question. Do we not understand the particle, or do we not understand the source? Perhaps the acceleration mechanisms within these galactic jets are far more efficient and powerful than we've ever dreamed. Maybe there are hidden processes, pockets of extreme magnetic reconnection, or undiscovered types of shockwaves within Centaurus A's jets that can kick particles to these unbelievable energies. Alternatively, the issue might lie with the particle's journey. Could the galactic and intergalactic magnetic fields between us and Centaurus have acted as a giant lens, focusing and bending the path of a particle from an even more distant and powerful event, making it only appear to come from our nearby neighbor? This would mean we're being tricked by the cosmos, a case of mistaken celestial identity. The Centaurus event stands as a crucial lesson in humility. It showed us that even when we think we found an answer, the universe might simply be showing us a more complex version of the question. It proved that a known source can still produce unknown physics, and that the greatest enigmas aren't always found in the deepest voids. Sometimes they're hiding in plain sight, emanating from the very objects we thought we understood. This brings us to a cosmic ray that didn't just challenge our ideas about where these particles come from, but how they even managed to survive the journey. We call this one the horizon skimmer, a particle whose very path through the cosmos seemed to flirt with impossibility. Detected with an energy that should have made it a prisoner to the laws of physics, this ultra-high-energy ray appeared to have traveled an immense distance, skimming through the thin, cold haze of the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. And according to everything we know, that journey should have been utterly fatal. To understand why, picture the universe not as a perfect vacuum, but as being filled with an incredibly sparse sea of light. This is the cosmic microwave background, a relic from the universe's infancy. For a proton traveling at nearly the speed of light, these photons aren't just background noise, they're like a constant, gentle rain. For most cosmic rays, this rain is barely noticeable. But for a particle with ultra-high energy, each tiny collision is a significant event. It's the physics equivalent of a high-speed motorcycle trying to race through a downpour. Every single raindrop stings, and over a long enough distance, the cumulative effect will slow the rider down dramatically. This is the GZK cutoff we mentioned earlier, a fundamental speed limit for the cosmic highway. A particle like the horizon skimmer, arriving with the energy it had, should have exhausted its entire fuel tank on the long road to Earth, bleeding its energy away in countless collisions with these ancient photons until it was just another slow-moving particle in the crowd. But the horizon skimmer did arrive, and its energy signature told a story that directly contradicts this expectation. The data suggested it had interacted with the microwave background in ways that were subtly but distinctly off. The particle's energy loss profile, the specific way it shed energy during its journey, didn't match the predictions of our standard particle physics models. It was as if the particle had a kind of shielding, or perhaps the photons of the background radiation behaved differently than we thought when struck by such an extraordinarily energetic projectile. This anomaly points to one of two thrilling and equally profound possibilities. The first is that our measurement of its energy or trajectory was somehow flawed, a simple error in the complex chain of detection and analysis. The second, far more exciting possibility is that we are seeing the fingerprints of new physics. This suggestion of new physics opens a door to realms of speculation that were once purely theoretical. Could it be that at these extreme energies, particles behave in ways not described by our standard model? Perhaps they interact with space-time itself differently, or there are unknown quantum properties that become significant only at these unimaginable scales. Some theorists have even proposed that such particles could be evidence of extraspatial dimensions, which would alter the fundamental forces at play during these high-energy collisions and allow the particle to conserve its energy more effectively over vast distances. The horizon skimmer, therefore, is more than just a mysterious detection. It's a potential Rosetta Stone. It challenges us to look beyond our current textbooks and consider that the rules of the universe, as we have written them, might only be a simplified version of a far more complex and astonishing set of laws waiting to be discovered. Now, let's consider a pair of cosmic rays that didn't just challenge our models of physics, but our understanding of time itself. We're talking about two specific particles detected years apart that seem to be cosmic twins. They arrived from the exact same patch of sky, and when scientists analyzed them, they found their energy signatures were nearly identical. This wasn't a case of two similar-looking events. It was a precise match, like receiving two bullets fired from the same gun but years apart. This is the mystery of the time-delayed duo. The sheer unlikelihood of this happening by pure chance is astronomical. The sky is vast, and the possible energy levels these particles can have are spread across an enormous range. For two independent, random events to share both a precise direction and an almost identical energy is a coincidence so staggering that it forces scientists to consider a far more exciting explanation: that these two particles did not come from a random, one-off cataclysm, but from a source that is periodically active, a cosmic engine that turns on, fires a particle of a specific energy. Then, years later, does it again. This shifts the entire investigation from looking for a catastrophic explosion to hunting for a repeating signal, a beacon in the cosmos. This possibility immediately narrows the field of potential suspects. A supernova, for instance, is a single, brilliant, and final event. It cannot produce a second, identical cosmic ray years later. The same goes for a gamma-ray burst or the merger of two neutron stars. These are singular cataclysms. A repeating source points to something far more stable and long-lived, yet capable of generating unimaginable power in bursts. The prime candidate becomes an active galactic nucleus where a supermassive black hole is actively feeding on surrounding matter. These systems are not static. Their accretion disks can have instabilities, their jets can flicker and flare. It is entirely plausible that such an engine could have a major outburst, accelerate a particle to a specific energy, and then, after a period of quiet, have another outburst that does the exact same thing. But the implications of a repeating source are even more profound than just identifying a culprit. If we can confirm that a specific celestial object is capable of producing these ultra-high-energy particles in repeated bursts, it would give us an unprecedented laboratory to study them. Instead of waiting for random, unpredictable events, we could point our most sensitive telescopes at that location and wait for the next one. We could study the environment in extreme detail, correlating the arrival of a cosmic ray with a specific flare in the jet of a black hole or a surge in gamma-ray emissions. This would move the field from pure detective work into a new era of observational astrophysics, allowing us to finally understand the mechanics of nature's most powerful particle accelerators. Of course, the haunting alternative is that this is in fact just a 1 in a billion fluke, a cruel trick of statistics. The universe is vast, and given enough time, even the most improbable events will eventually occur. If that's the case, then these two cosmic twins are a beautiful but meaningless coincidence, a reminder that patterns can emerge from randomness, and that our human tendency to find signals in the noise can sometimes lead us down fascinating but ultimately empty paths. Whether they are a genuine repeating signal or a statistical phantom, the time-delayed duo masterfully illustrates the constant tension in cosmic ray astronomy between profound discovery and perplexing coincidence, keeping researchers forever on the edge of a major breakthrough. Now, let's turn our attention to a cosmic ray that didn't just defy the laws of physics, but the very maps we use to navigate the cosmos. We call this one the magnetic rebel. Unlike the particles that arrive from seemingly empty voids, this ultra-high-energy cosmic ray presented a different kind of puzzle. Its path to Earth was anything but straight. It was a twisted, convoluted journey, bent and shaped by the invisible magnetic fields that weave through our galaxy. For scientists, this bending is normally a key to solving the mystery. By understanding the strength and structure of these fields, they can trace the particle's path backwards, like rewinding a tangled ball of yarn to find its point of origin. But with the magnetic rebel, that process led to a dead end, revealing just how much we still have to learn about the invisible forces that fill our galaxy. The challenge begins with the sheer power of the particle itself. Galactic magnetic fields, while incredibly complex, are also incredibly weak. Their ability to bend the path of an incoming particle depends directly on that particle's energy. A low-energy cosmic ray is like a tiny paper boat on a rushing river, easily tossed and turned by every ripple and current. It can be deflected by dozens of degrees, making its original direction almost impossible to determine. An ultra-high-energy cosmic ray, however, is different. It's like a massive ocean liner plowing through the same river. It has so much momentum that the tiny currents barely affect its course. It should travel in a nearly straight line, giving researchers a much clearer shot at pinpointing its source. The magnetic rebel had that kind of energy, which meant its path, while bent, should have been predictable based on our best models of the Milky Way's magnetic landscape. But when scientists applied those models to backtrack this particle, something was clearly wrong. The calculated path didn't lead to a brilliant quasar, a violent supernova remnant, or any other logical cosmic accelerator. Instead, it pointed to a region of space that was, for all intents and purposes, unremarkable. A blank spot on the celestial map. This left the research team with a deeply unsettling conclusion. Either our map of the galactic magnetic fields is fundamentally incorrect, or the source of this particle is an astronomical object so exotic that it doesn't register on any of our instruments. Both possibilities are equally thrilling and humbling for the field of astrophysics. This single detection exposes a critical blind spot in our quest to understand the universe. We can build enormous detectors to catch these particles and powerful telescopes to scan the heavens, but if we don't understand the magnetic maze they travel through, we're trying to solve a puzzle with half the pieces missing. Our current maps of the Milky Way's magnetic field are like early charts of the ocean based on scattered measurements and informed guesswork, but filled with vast, unexplored regions where dragons might indeed dwell. The path of the magnetic rebel suggests that in some parts of our galaxy, the magnetic fields could be significantly stronger, weaker, or tangled in ways we haven't yet imagined. These invisible structures could be sculpted by the pressure of stellar winds, the shock waves from ancient supernova, or the gravitational influence of dark matter, creating magnetic corridors and dead zones that completely alter a particle's journey. The other side of this coin is even more provocative. What if our magnetic maps are mostly correct and the backtracking is accurate? That would mean the source is truly there in that empty patch of sky, but completely invisible to us. This opens the door to the existence of what astronomers call dark sources. These could be rogue black holes drifting silently through space, dense clumps of dark matter annihilating and releasing immense energy, or stellar corpses like neutron stars that have grown cold and dark but retain unimaginably powerful magnetic engines. The magnetic rebel, therefore, is a dual messenger. It's not only a particle of incredible energy, it's a probe that has sampled the hidden magnetic geography of our galaxy and returned with data we are only just beginning to decipher, forcing us to admit that the space between the stars is far from empty and far from understood. Now we encounter a cosmic ray that presents a different kind of puzzle, one that doesn't defy the laws of physics outright, but instead seems to find a loophole in them. This is the story of the energy outlier, a particle detected with an energy value that sits precisely at the theoretical limit known as the GZK cutoff. This isn't a particle that breaks the speed limit, it's one that cruises right at the maximum allowed speed, and its very existence in such numbers forces us to question whether the rules of the cosmic road are exactly as we've written them. To appreciate why this is so strange, we need to revisit the concept of the GZK cutoff. Imagine a long-distance runner attempting a marathon through a continuous, gentle headwind. The headwind represents the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills every cubic inch of space. For a proton, this headwind creates a drag force. The faster the runner goes, the harder the wind pushes back, sapping their energy with every step. The GZK cutoff is the theoretical point where the headwind becomes so punishing that the runner cannot possibly maintain that pace over an intergalactic distance. They would simply run out of energy long before the finish line. Particles with energies above this limit, like the oh my god particle, are the shocking rule breakers. But particles at this precise limit should be incredibly rare travelers, because the physics suggests it's almost impossible for them to arrive from far away without losing just a little bit of energy along the journey. Yet, that's not what our detectors are telling us. The energy outlier and other particles like it are not the rare, exotic exceptions we expected. Instead, they are being detected with a frequency that is noticeably higher than our models predict. It's as if the marathon organizers expected only a handful of elite athletes to even attempt the race, but on the day of the event, a steady stream of runners is crossing the finish line right at the time limit. This discrepancy is a major clue that our understanding of the race itself, the interaction between high-energy particles and the cosmic microwave background, might be flawed or incomplete. This anomaly points directly at the theory of GZK suppression itself. For decades, this theory has been a cornerstone of cosmic ray physics, a well-respected barrier that defines what is possible. The higher-than-expected detection rate of particles at this energy suggests that the suppression effect might not be as strong as we've calculated. Perhaps the headwind isn't quite as strong as we think. Maybe the particles are more efficient runners, finding ways to conserve their energy that we haven't accounted for in our models. This opens up a realm of fascinating possibilities that could reshape fundamental physics. One compelling idea is that our inventory of the universe's particles might be incomplete. The standard model of particle physics has been incredibly successful, but it doesn't explain everything. The energy outlier could be a hint of something new. What if this cosmic ray wasn't a simple proton, but a heavier nucleus like that of iron or oxygen? A heavier particle would interact differently with the microwave background photons, potentially experiencing less drag over the same distance and allowing it to arrive at Earth with its energy intact more easily than a proton could. Alternatively, some theorists propose that these particles could be something entirely exotic, like a neutrino with unusual properties that allow it to slip through the cosmic haze almost untouched. The implications of this are profound. If the GZK suppression is weaker than we believe, it means that the universe's most powerful particle accelerators could be much farther away than we thought. We might be detecting particles from cataclysmic events in galaxies halfway across the observable universe, dramatically expanding the potential pool of sources we need to consider. The energy outlier, therefore, is a quiet revolutionary. It doesn't arrive with the staggering, record-breaking power of its more famous cousins, but its persistent, statistically significant presence is a powerful signal that we are on the verge of rewriting the textbooks on how the most energetic particles in the universe travel across the vast expanses of space and time. While the raw energy of a cosmic ray is often the headline, sometimes the real story is written in the subtle details of its composition. This brings us to two specific detections, cosmic rays 14 and 15, which presented a puzzle not of power but of identity. These particles arrived and struck our atmosphere, creating the usual cascading shower of secondary particles that our observatories are designed to detect. But when scientists analyzed the debris from these collisions, they found something that made them look twice. The isotopic signature, the specific blend of atomic variants within the shower, was all wrong. It was an anomaly that pointed not to a failure of our acceleration models, but to a gap in our understanding of the cosmic rays themselves and the long, strange journey they take to reach us. To understand why this is so significant, think of a cosmic ray as a messenger. Its energy tells us about the power of the cannon that fired it. Its direction offers a clue, however fuzzy, to the cannon's location. But its composition, the very stuff it's made of, is its passport, carrying stamps from its origin and every place it has visited on its way to us. The vast majority of cosmic rays are simple protons, the naked nuclei of hydrogen atoms. Others are heavier elements like helium, carbon, or iron. And each of these elements comes in different isotopes, versions of the same element that have a different number of neutrons in their nucleus. The ratio of these isotopes is like a fingerprint. We have a very good idea of what this fingerprint should look like based on the composition of our own solar system and the general interstellar medium. These two cosmic rays had fingerprints that didn't match any known records. This isotopic anomaly forces us to consider two radically different explanations, each with profound implications. The first possibility is that these particles were born in an environment that is fundamentally unlike anything we see nearby. Their unusual isotopic makeup could be a direct signature of an exotic source. Imagine a star that lived and died in a way completely different from the stars in our galactic neighborhood. Perhaps it was a rare hypernova, an event even more violent than a typical supernova, forging elements in a unique crucible of pressure and heat that created an abnormal blend of isotopes. Or maybe the source is something even more esoteric, like the jet of a supermassive black hole that is actively consuming a star with a very peculiar composition. In this scenario, the anomaly is a pristine clue, a direct sample from a type of astrophysical factory we have never before observed. The second, and perhaps even more mind-bending, possibility is that the particles started their journey with a normal composition, but it was changed along the way. Cosmic rays don't travel through a perfect vacuum. They voyage through a galaxy filled with thin gas and dust. As a heavy nucleus like iron zooms through this material at nearly the speed of light, it can occasionally slam into the nucleus of a sedentary atom in interstellar space. These collisions are incredibly violent and can literally chip pieces off the traveling cosmic ray, changing a nucleus of one isotope into another. This process, called spallation, acts like a kind of cosmic erosion, slowly sculpting and altering the particle's original identity over millions of years. If spallation is the cause, then these isotopic anomalies are not a sign of the source, but a detailed map of the particle's journey. The specific changes to its composition would tell us exactly how much material it has traveled through, offering a unique way to measure the density of the interstellar medium along its path. This would turn the cosmic ray from a simple messenger into a sophisticated probe, allowing us to chart the otherwise invisible structure of our galaxy. The problem is that our current models of spallation and galactic material density can't fully account for the weird ratios we see. Either our maps of the galaxy's matter are wrong, or our understanding of the nuclear physics involved in these high-speed collisions is incomplete. These two particles, with their cryptic isotopic codes, challenge us to become better forensic scientists of the cosmos, reminding us that every piece of data, no matter how small, can contain a universe of meaning. While most ultra-high-energy cosmic rays announce their arrival with a spectacular aerial fireworks show, one particular particle decided to break the rules entirely. This is the story of the silent messenger, a cosmic ray that arrived with immense energy but left behind a ghostly signature, challenging not just our theories but the very tools we use to detect them. When a typical high-energy particle strikes the top of our atmosphere, it doesn't just hit and stop, it triggers an avalanche. It slams into an air molecule, which shatters and creates a shower of secondary particles, muons, electrons, photons, that rain down over a wide area on the ground. Our observatories are designed to catch this expansive shower, using an array of detectors spread across miles of desert to piece together the energy and direction of the original cosmic ray. It's a well-understood process, the foundation of how we've studied these particles for decades, but the silent messenger didn't play by these rules. This particle arrived, but it failed to produce the expected cascade. The signal it created was faint, isolated, and incredibly difficult to distinguish from background noise. It was like hearing a single, powerful footstep in a quiet forest instead of the crashing of a falling tree. For the scientists analyzing the data, this presented an immediate crisis of interpretation. Without the rich data from a full particle shower, how could they be certain of the particle's true energy? How could they accurately trace its path back through the galaxy? The very integrity of the detection was called into question. Could it have been a glitch, a rare fluctuation in the detector itself, or was it a genuine cosmic event that revealed a gap in our understanding of how matter and energy interact at the most extreme scales? The existence of such dry events, as researchers sometimes call them, forces a profound evolution in both technology and theory. On the technical side, the silent messenger is a stark warning that our current detector arrays might be blind to a whole class of cosmic rays. If a particle can arrive without creating a traditional shower, how many have we missed over the years? This realization drives the need for next-generation observatories that are more sensitive and can detect multiple types of signals simultaneously. It pushes innovation, leading to the development of hybrid detectors that combine traditional particle counters with fluorescence telescopes that watch for the faint ultraviolet light emitted by even the most hesitant showers, ensuring that no messenger from the cosmos goes unheard. On the theoretical side, this quiet arrival demands an explanation. Why would a particle with so much energy fail to interact? One possibility is that we're not dealing with a proton or a heavy nucleus at all. The culprit could be a different type of particle entirely. The prime suspect is a neutrino, an infamous ghost particle with almost no mass and that famously barely interacts with normal matter. A neutrino with ultra-high energy could, in theory, travel deep into our atmosphere before finally deciding to interact with an atom, creating a much smaller, more contained burst of particles that is easily missed. If confirmed, this would be a landmark discovery. Detecting an ultra-high-energy neutrino from deep space would open an entirely new window on the universe, as these particles can travel straight from the hearts of the most extreme environments without being deflected by magnetic fields. The silent messenger, therefore, is a paradox. Its very weakness as a detectable signal is its greatest strength as a scientific catalyst. It serves as a powerful reminder that the universe doesn't always communicate in ways we expect, and that the path to discovery often requires us to build better ears to listen. It challenges the entire field to be more clever, more precise, and more open to the unexpected, proving that sometimes the most important messages are delivered in a whisper. Then we have a particle that seemed to play by its own rules of travel, a cosmic ray we call the speed Defy. This detection didn't challenge the ultimate cosmic speed limit. The speed of light remains unbroken, but it did appear to bend the rules of the long-distance race across the galaxy. When scientists analyzed its energy and its precise time of arrival, a small but significant anomaly emerged. The journey of this particle, from its suspected source to our detectors on Earth, seemed to have taken just a little less time than our most reliable models predicted. It was as if a commuter on a well-traveled route with known traffic patterns arrived home consistently 5 minutes early day after day, suggesting there might be a hidden shortcut or a flaw in our understanding of the road itself. This subtle discrepancy sends physicists scrambling not for entirely new laws of physics, but for a finer tooth comb to examine the details of the existing ones. The key to this mystery lies in the intricate dance between a cosmic ray and the environment it travels through. Space is not a perfect vacuum. It's filled with the interstellar medium, a sparse soup of gas, dust, and crucially, a complex web of magnetic fields. These fields, though incredibly weak, are everywhere, and they don't act as a drag on a particle's speed. Instead, they act as a labyrinth, forcing the charged particle to zig and zag on its million-year journey. A cosmic ray doesn't travel in a straight line. It corkscrews along magnetic field lines, tracing a path that is vastly longer than the direct geometric distance from its source. The apparent, faster-than-expected arrival of the speed Defy suggests that our maps of this magnetic labyrinth might be incomplete or inaccurate. Perhaps the magnetic fields along its particular path are slightly weaker than we've modeled, allowing for a tighter, more efficient spiral and a slightly quicker overall transit time. Or maybe the fields are aligned in a way that, by pure chance, created a more direct corridor for this one particle, a lucky break in the cosmic maze that shaved a tiny fraction off its travel time. This turns the speed Defy from a mere particle into a valuable probe, its journey providing a unique data point to help us chart the invisible magnetic structures that weave between the stars, refining our models of the galaxy's hidden architecture. The other compelling possibility involves the nuances of relativity itself. While the particle's average speed over its entire journey is what we calculate, its instantaneous speed as it traveled through different densities of the interstellar medium would have varied in incredibly complex ways. The energy loss mechanisms from interactions with sparse gas could be ever so slightly different than our formulas account for. Investigating this anomaly forces a meticulous review of these relativistic corrections, the tiny, often ignored second-order effects that become noticeable only when dealing with such precise measurements across such vast distances. The speed Defy, therefore, is a testament to the increasing precision of our science. We are now measuring these cosmic journeys with such exactness that we can detect deviations that would have been completely invisible just a decade ago, pushing us to understand not just the broad strokes of the universe's laws, but the finest print written within them. And now we arrive at a mystery that is perhaps the most profound of all, a challenge so fundamental it comes not from a single particle, but from a trio of them acting in concert. Cosmic rays 18, 19, and 20 were all detected by the colossal Pierre Auger Observatory in Argentina, an instrument so vast it covers 3,000 square kilometers of the Pampa Amarilla, an area nearly the size of Rhode Island. This immense array is our most powerful net for catching the universe's most energetic particles, and what it caught with these three was a pattern of pure enigma. Each of these ultra-high-energy cosmic rays arrived with power that should mark them as products of the most violent places in the universe. Yet, when researchers performed the now familiar ritual of tracing their paths backward through the galaxy and out into intergalactic space, all three trails led to the same bewildering conclusion: a vast, cold, and utterly empty intergalactic void. The sheer scale of this nothingness is difficult to overstate. We are not talking about a simple gap between two stars in our own galaxy. These are cosmological voids, the universe's true deserts. They are immense regions of space, often spanning tens of millions of light years, that are largely devoid of the galaxy's gas clouds and dark matter filaments that make up the cosmic web. Finding a source for these particles here is the ultimate contradiction in terms. It's the astrophysical equivalent of finding a fully operational, state-of-the-art car factory in the middle of the Sahara Desert, with no roads leading in or out, no supply chains, and no source of power. The very laws of physics, as we understand them, insist that such a place cannot host the engine required for this incredible feat of particle acceleration. This forces us into a corner where we must consider possibilities that range from the revolutionary to the nearly miraculous. One theory suggests that these voids are not truly empty. They might be home to immense but invisible structures made of dark matter. We know this mysterious substance vastly outweighs normal matter in the universe, and it could be clumped together in ways we cannot directly see. Perhaps within these voids, dense knots of dark matter are colliding and annihilating, converting their mass directly into energy and firing off ultra-high-energy protons in the process. This would be a hidden, dark universe operating in parallel to our own, its most dramatic events only revealed when a stray particle accidentally crosses into our visible realm. Another, even more mind-bending idea is that our understanding of magnetic fields is not just incomplete within our galaxy, but on a cosmological scale. The space between galaxies is threaded with magnetic fields, but we have almost no data on their strength or structure in these immense voids. Could it be that these fields are not weak and disorganized, but are instead shaped into colossal, focused structures? Picture a magnetic funnel or a cosmic-sized particle accelerator tube, stretching across millions of light-years of emptiness. If such a structure existed, it could, in theory, grab a particle from a distant, powerful event and focus its energy, acting as a magnetic lens that both accelerates it and bends its path to make it appear it came from nowhere. The particle's true origin would be masked, and we would be left staring at the empty end of the universe's most powerful hose. The existence of this trio from nowhere is arguably the most elegant and frustrating argument for new physics. They represent a statistical reality that is impossible to ignore. Three independent events, all from similar empty regions, cannot be easily dismissed as a fluke. They form a pattern that our current models of the universe are utterly unequipped to explain. They stand as a silent, three-part rebuke to our assumptions, a clear signal that our maps of the cosmos are missing entire categories of landmarks. We have charted the galaxies and the stars, but we have failed to understand the deserts between them, and it is from these great nothings that the universe is sending its most energetic and most mysterious messages. While the cosmos is filled with particles of all energies, one detection stands apart not for its raw power but for its profound age. This specific cosmic ray, which we'll call the Ancient Ray, carried an energy signature that told a story of an almost unimaginable journey. When researchers analyzed its properties, they concluded that this particle had likely been traveling for billions of years, a solitary messenger from a time when the universe itself was young, perhaps even before our own solar system had begun to form. It was a fossil, preserved not in rock but in motion, offering a direct window into the ancient cosmos. This idea of a multi-billion-year journey immediately introduces a major complication rooted in the very expansion of the universe. Billions of years ago, the cosmos was a much denser, hotter, and more crowded place. The faint haze of the cosmic microwave background radiation, which today acts as a gentle headwind for traveling particles, was far more intense and potent in the early universe. For a proton to survive a journey from that era to the present day is like expecting a paper boat to survive a voyage across a stormy, primordial ocean and arrive on a modern shore completely dry. According to our standard models of particle physics and cosmology, the relentless battering from this denser radiation field should have bled the ancient ray of all its energy eons before it could ever reach our detectors. The fact that it arrived with a significant amount of energy still intact is a direct challenge to our calculations of how matter and energy interact across cosmological timescales. This paradox forces us to confront two deeply fascinating possibilities. The first is that the source of this particle was not just powerful, but unimaginably, cataclysmically powerful. An event so energetic that it could launch a particle with such an excessive amount of raw force that even billions of years of travel through a hostile, young universe couldn't completely stop it. We have no known astrophysical object in the modern universe that fits this description, which suggests that the early universe might have been home to types of cosmic engines that no longer exist today. Theorists speculate about hyper-efficient active galactic nuclei fueled by faster-feeding black holes, or incredibly rare and violent phenomena like the collapse of supermassive stars, events so extreme they make modern supernova look like firecrackers. The ancient ray could be the last remaining ember from a type of fire that burned only once at the dawn of time. The second, and even more profound, possibility is that our understanding of the early universe's environment is flawed. Our models of how the density and temperature of the cosmic microwave background have evolved over time are based on a very successful and robust cosmological framework. But the arrival of this particle suggests there might be a missing piece. Perhaps the radiation field was not quite as uniform or as intense as we've calculated in certain regions of space, creating rare, clear pathways that a particle could traverse with less energy lost. Or maybe the physics of how ultra-high-energy protons interact with photons is subtly different at these extreme energies than our laboratory experiments can predict. The ancient ray, therefore, acts as a unique calibration tool, a natural experiment that tests our models of the universe's conditions billions of years in the past. Ultimately, this single particle does more than just add to the mystery of cosmic rays. It connects our present to the deep past in a startlingly direct way. It forces cosmologists to reconsider the universe's energy budget across eons, questioning whether the most powerful events in cosmic history were even more energetic than we've dared to imagine. The ancient ray is a relic that shouldn't exist, a whisper from an epoch of unparalleled violence that has somehow survived the unimaginable journey to our doorstep, challenging us to rewrite the story of the universe's youth. But our planet's geography itself presents a unique challenge in this cosmic detective hunt, a problem perfectly illustrated by the case of the polar wanderer. This particular ultra-high-energy cosmic ray didn't arrive from the void or a distant galaxy. Its trajectory pointed back to a region near one of our celestial poles. For astronomers, this is one of the most frustrating and difficult places on the entire sky to get a clear reading, not because of anything in space, but because of the limitations of our own observatories here on Earth. The world's largest cosmic ray detectors, like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah, are magnificent scientific instruments, but they are fixed in place on the ground. Their location in the southern and northern hemispheres, respectively, means they have an inherent blind spot. They are designed to stare most effectively at the sky directly above them, and their view of the horizons, particularly near the poles, becomes increasingly sparse and unreliable. Detecting a cosmic ray from near the pole is like trying to spot a single, specific bird in a massive flock, while only being able to look through a narrow tube pointed almost straight up. You might catch a glimpse of it if it flies right through your line of sight, but you'll miss almost everything happening around the edges. For the polar wanderer, this sparse detector coverage created a cascade of uncertainty. The array only caught a partial signal of the particle shower it created. This made pinning down its exact energy incredibly difficult. Without multiple detectors catching the full extent of the shower, the energy estimate has a much larger margin of error. Was it truly an ultra-high-energy event or just a very high-energy one? The data was too fuzzy to say for sure. Furthermore, tracing its path backwards became a monumental task. The magnetic fields of Earth and the galaxy bend the paths of these charged particles, and with only a few data points from the edge of the detector array, calculating that original direction is like trying to map the entire route of a cross-country road trip based on a single, blurry photo taken from a highway off-ramp. This single, frustrating detection exposes a critical and often overlooked truth in astronomy. Our view of the universe is profoundly shaped by our own vantage point. We don't have a perfectly neutral, all-seeing eye. Our observational networks have built-in biases. We see some parts of the sky with crystal clarity and others only through a foggy, distorted lens. The celestial poles are cosmic dead zones in our data, not because nothing happens there, but because we are poorly equipped to see it. This means there could be an entire class of cosmic rays, perhaps even a significant number of them originating from sources near these poles that we are almost completely missing. We might be dramatically underestimating how common these events are, or we could be missing a key source region entirely because it happens to lie in a part of the sky our best tools can't properly scan. The polar wanderer, therefore, is a humbling messenger. Its value isn't in answering a question, but in highlighting a flaw in our approach. It serves as a powerful argument for the next generation of cosmic ray astronomy, a global network of detectors or space-based observatories that can truly watch the entire sky, leaving no corner unobserved. It reminds us that to solve the mysteries of the cosmos, we must first acknowledge and overcome the limitations of our own earthly perspective. Moving from the frustrating blind spots of our own planet to the crowded heart of the cosmos, we encounter a cosmic ray that presents a tantalizing contradiction. a particle that seems to come from a known location, but in doing so defies our understanding of that very place. This is the story of the cluster candidate, a ray whose detected path pointed back toward a massive galaxy cluster, a dense congregation of hundreds or even thousands of galaxies bound together by gravity. On the surface, this seems like a perfect match. Galaxy clusters are chaotic, energetic environments filled with the turbulent gas, powerful shock waves, and immense magnetic fields that should, in theory, make them ideal cosmic particle accelerators. But the devil, as always, is in the details, and the details of this detection ignited a fierce debate about the very nature of these colossal structures. The central problem isn't that the cluster accelerated the particle, it's that the cluster should have also stopped it. Imagine a magnificent cannon built inside a massive, dense fortress. The cannon is powerful enough to fire a cannonball with incredible force, but the fortress walls are so thick that any cannonball fired from within would be absorbed by the inner ramparts long before it could ever escape to the outside world. This is the paradox of the cluster candidate. Galaxy clusters are not just collections of galaxies, they are also filled with an incredibly hot, thin plasma known as the intracluster medium. This superheated gas is seething with powerful magnetic fields, and it fills the entire space between the galaxies in the cluster. For a proton traveling through this environment, it's like trying to run through a swimming pool filled with molasses and crisscrossed with powerful, invisible barriers. According to our best models, a cosmic ray generated within a galaxy cluster, perhaps by a supernova in one of its member galaxies or by activity around a central supermassive black hole, should lose a significant amount of its energy as it tries to fight its way out. The particle should be scattered, absorbed, and slowed down by countless collisions with the intracluster gas and by the twisting magnetic fields that force it to take a long, convoluted path. By the time it could potentially escape the cluster's gravitational and magnetic grip, it should have been reduced to a much lower energy level. The cluster candidate, however, arrived with energy that was suspiciously high, as if it had been fired from that cannon and passed through the fortress walls as if they weren't even there. This leaves scientists with two equally compelling but opposing explanations, each championed by different factions within the astrophysics community. The first camp argues that we are fundamentally overestimating the stopping power of galaxy clusters. They propose that our models of the intracluster medium are too simplistic. Perhaps the gas is not as uniformly dense as we think, and the cosmic ray found a lucky path through a more sparse region, a cosmic loophole that allowed it to slip through with minimal energy loss. Maybe the magnetic fields, while powerful, are structured in a way that can sometimes focus and channel particles, acting less like a barrier and more like a particle guide, efficiently funneling them out of the cluster like a magnetic railgun. If this is true, then galaxy clusters could indeed be the long-sought factories for these ultra-high-energy particles, and we simply need to refine our understanding of their complex internal physics. The other camp, however, sees this as evidence for a far more exotic scenario. They argue that the cluster is not the source at all, but merely a signpost. In this view, the cosmic ray was produced by something far beyond the cluster, something even more powerful and distant. As it traveled across the universe, its path was bent by the immense gravitational field of the galaxy cluster. Gravity can act as a lens, warping the fabric of space-time and altering the trajectory of anything passing by, including light and, of course, particles. The cluster candidate's path, therefore, wouldn't point to its true origin, but would instead be drawn toward the cluster's overwhelming gravitational pull, making it appear as if it came from there. This would mean the cluster is an innocent bystander, its presence creating a cosmic mirage that has misled our detective work. This debate gets to the very heart of the scientific process. The cluster candidate is not just a data point, it's a catalyst. It forces researchers on both sides to sharpen their models, to run more sophisticated simulations of particle propagation through magnetized plasma, and to develop new methods for untangling the effects of gravity on these charged messengers. It exemplifies how a single, stubborn anomaly can drive an entire field forward, proving that sometimes the most valuable discoveries are the ones that don't neatly fit, the ones that compel us to question not just what we see, but how we see it. And sometimes the universe doesn't send a single messenger. It sends a pair, a 1-2 punch that arrives so close together, it forces us to reconsider the very nature of these cosmic events. This is the story behind cosmic rays 24 and 25, two ultra-high-energy particles that struck our atmosphere within mere seconds of each other. For the scientists monitoring the detectors, this wasn't just another data point. It was a moment of electrifying synchrony. The odds of two independent, random cosmic rays of such extreme energy arriving within such a narrow window of time are astronomically low, suggesting these two particles were not a coincidence but were almost certainly siblings, two pieces of debris launched from the same cataclysmic event across the vastness of space. This rare double impact immediately shifts the entire investigation from a question of what to a question of how. How does a cosmic engine produce multiple ultra-high-energy particles at essentially the same moment? The answer to this question holds the key to understanding whether these enigmatic sources operate like a sudden, violent explosion or like a steady, continuous beam. Most of the violent events we know of in the universe are transient bursts. A supernova is a singular, brilliant flash. A gamma-ray burst is a blindingly intense but fleeting beam of energy. These are one-off events, cosmic lightning strikes. If they are the source, then the detection of two particles would imply that the explosion was not only unimaginably powerful, but also incredibly efficient at accelerating not just one, but a whole swarm of particles to these unbelievable energies in a single, instantaneous burst. It would be the difference between a cannon firing a single cannonball and a cannon firing a tightly packed volley of them all at once. The alternative is a source that isn't a brief explosion at all, but a sustained and stable accelerator. This is where the idea of an active galactic nucleus becomes so compelling. Picture the jet of a supermassive black hole not as a single explosion, but as a continuous, high-energy river of plasma flowing outwards for millions of years. Within this relentless flow, there could be moments of intense turbulence, shockwaves, and magnetic instabilities that act like individual power boosters along the pipeline. These sub-events could kick groups of particles to ultra-high energies in quick succession. In this scenario, the double impact we detected wouldn't be the entire output of a single explosion, but rather two particles that happened to get accelerated by the same shockwave within the jet and then traveled along nearly identical paths to reach us almost simultaneously. This paints a picture of a more controlled, long-lived factory rather than a brief, chaotic detonation. The implications of this distinction are enormous for our ability to ever pinpoint these sources. A burst-like source is here one moment and gone the next. By the time its particles travel for millions of years to reach us, the source itself may have long since faded into obscurity, leaving behind no visible trace for our telescopes to find. This would explain why so many cosmic rays seem to come from nowhere. Their source simply doesn't exist anymore. A continuous source, however, is a constant beacon. If a specific active galaxy or other persistent object is identified as the origin for a doublet or even a larger group of particles, we could then train every available telescope on that location, watching for correlated activity, a flare in its jet or a surge in its gamma-ray output that coincides with the arrival of a cosmic ray here on Earth. This would finally give us the crucial link between the detection of the particle and the observation of the accelerating event itself. The detection of this double impact is a gift wrapped in a mystery. It provides a precious clue that these particles might not always travel alone, offering a new statistical handle on their origins. It forces models of particle acceleration to account for the possibility of multiple, near-simultaneous ejections, constraining the power and the duration of the events that create them. Whether from a fleeting burst or a steady flow, these two cosmic rays that arrived hand in hand remind us that the universe's most powerful engines operate on a scale where the rules are still being written, capable of launching salvos of energy that cross the cosmos to deliver their message in unison. But the universe has more than one way to send a message, and sometimes it communicates across multiple channels at once. This brings us to a truly special event, Cosmic Ray 26, a detection that wasn't just seen by one type of instrument but was heard as well. When this ultra-high-energy particle slammed into our atmosphere, it did more than create a shower of secondary particles. It generated a faint, telltale whisper in the radio spectrum. As the cascade of electrons and positrons from the air shower raced downward, they interacted with Earth's magnetic field, producing a brief but distinct pulse of low-frequency radio waves. This signal was picked up by sensitive radio telescopes, making this a multi-messenger event, a cosmic ray that announced its arrival with both a particle shower and an electromagnetic echo. For astronomers, catching an event like this is the equivalent of striking gold. Normally, detecting a cosmic ray is a one-dimensional experience. You get a measurement of its energy and a rough, often ambiguous direction of arrival. It's like hearing a loud bang from another room. You know something happened, but you have no idea what caused it. The addition of the radio signal adds a whole new layer of data. By combining the information from the particle detectors with the radio pulse, scientists can triangulate the cosmic ray's path with far greater precision. It's the difference between hearing that bang and also seeing a flash of light from the same direction. Suddenly, you have two independent clues to help you pinpoint the source. This powerful combination promised to cut through the uncertainty that has plagued so many other detections and finally point a definitive finger at a culprit. Yet, in a twist that has become hauntingly familiar in this field, even this richer, more complete dataset led to a dead end. The refined path, calculated with this new multi-messenger precision, was traced back through the galaxy and out into intergalactic space. Researchers eagerly followed this sharper trail, expecting it to lead to a brilliant active galaxy, a turbulent star-forming region, or at the very least a known celestial object. Instead, the path terminated in another patch of unremarkable, empty space. The combined power of particle physics and radio astronomy, two of our most advanced tools for probing the cosmos, had still failed to identify a source. The mystery hadn't been solved, it had simply been sharpened into a finer, more frustrating point. This result is profoundly humbling because it eliminates so many potential excuses. We can no longer blame the ambiguity solely on poor directional data or the distorting effect of galactic magnetic fields. The multi-messenger approach was supposed to correct for those very issues. The fact that even a high-precision trajectory leads to nowhere forces a much more radical conclusion, that the true accelerators of these particles are either completely invisible to our current suite of telescopes or are located in environments so unlike anything we know that we wouldn't recognize them as a source even if we were looking right at them. The low-frequency echo didn't provide the answer we hoped for, but it did provide something perhaps more valuable, a clearer, more undeniable statement of the problem, reminding us that some of the universe's greatest secrets are guarded by puzzles we are only just learning how to see. While every cosmic ray detection adds a piece to the puzzle, Cosmic Ray 27 seemed to break the puzzle itself. This particular particle didn't just challenge our ideas about where these rays come from. It challenged the very statistical rules that govern how they should behave. For decades, the foundational model for understanding cosmic rays has been the power law distribution. This elegant principle suggests that as the energy of cosmic rays increases, the number of particles we detect at that energy drops in a smooth, predictable curve. It's like saying for every 100 particles with a certain energy, you might find only one with 10 times that energy, and only one with 100 times that energy, following a consistent mathematical pattern. This model has been incredibly successful, applicable to everything from the rumble of city traffic to the output of the sun. But cosmic ray 27 and others like it arrived with an energy that represented a dramatic and sudden break in this smooth curve, a sharp, unexpected cliff in the data that scientists call a spectral break. This isn't just a minor statistical blip, it's a fundamental anomaly that forces a major rethink of cosmic ray theory. A smooth power law implies a single, dominant type of accelerator is at work, operating with consistent rules across a vast range of energies. A sharp break, however, is the universe's way of telling us that the rules have changed. It suggests that at a certain critical energy threshold, something profound happens. One compelling explanation is that we are seeing the signature of a brand new class of cosmic ray sources. Up to a certain energy, the particles we detect might be coming from one population of objects, say, supernova remnants within our own galaxy. But beyond that sharp break, the particles could be coming from an entirely different type of engine, something far more powerful and rare, like the jets from active galactic nuclei. The break, in this case, marks the energy point where the local accelerators can no longer compete, and the cosmic ones take over, resulting in a sudden, steep drop in the number of particles that can reach such incredible energies. The other thrilling possibility is that the break has nothing to do with the source and everything to do with the journey. This sharp drop-off could be the long-predicted but never conclusively observed fingerprint of the GZK suppression effect. It could be the precise energy point at which the cosmic microwave background radiation finally becomes an impenetrable barrier. Particles with energies just below this threshold can still travel meaningful intergalactic distances, while particles above it are almost completely attenuated, their numbers plummeting because they lose their energy long before they can reach our detectors. If this is true, then the spectrum breaker isn't an anomaly at all, but a remarkable confirmation of a decades-old prediction, finally made visible in a single telling data point. It would be the first direct observational evidence of this cosmic speed limit in action. However, the energy of cosmic ray 27 complicates this elegant explanation. Its specific value doesn't align perfectly with the theoretical predictions for the GZK cutoff for a simple proton. This misalignment opens the door to even more fascinating interpretations. Perhaps the particle wasn't a proton but a heavier nucleus like iron. A heavier nucleus would interact with the microwave background in a different way, experiencing the suppression effect at a higher total energy. The detected break, then, wouldn't be a universal barrier, but a barrier specific to a certain type of particle. This would mean our galaxy and others are not just accelerating protons, but also blasting out heavy nuclei at these unbelievable energies, and we are only now beginning to see the complex structure of their different journeys. The spectrum breaker, therefore, does more than just present a mystery, it provides a new analytical tool. By studying where these breaks occur in the energy spectrum, scientists can potentially identify the composition of ultra-high-energy cosmic rays without ever directly catching them, inferring the stuff they're made of from the subtle ways they obey, or defy, the predicted laws of their long journey through the cosmos. While most cosmic rays point to the chaotic hearts of galaxies or the vast emptiness of voids, one particular detection offers a clue that the source might not be made of normal matter at all. This particle, cosmic ray 28, arrived with all the hallmarks of an ultra-high-energy event, but its energy signature and trajectory were subtly different. When researchers attempted to trace its origin, they found nothing: no active galaxy, no star-forming region, not even an empty void. This complete lack of a conventional source, combined with its unique properties, has led some theorists to propose a radically different explanation. What if this particle wasn't accelerated by a cosmic engine, but was instead born from the invisible stuff that makes up most of the universe's mass? This is the compelling case for a dark matter candidate. The idea hinges on one of the greatest unsolved mysteries in all of science. We know from multiple lines of evidence, the rotation of galaxies, the bending of light, the large-scale structure of the cosmos, that about 85% of the matter in the universe is invisible. We call it dark matter. It doesn't emit, absorb, or reflect light, making it completely undetectable to our telescopes. We only know it's there because of its gravitational pull on the things we can see. For decades, physicists have been searching for any sign of what this mysterious substance actually is. One leading theory suggests that dark matter is not a single monolithic thing, but could be made up of a family of exotic particles, ones that rarely, if ever, interact with normal matter through any force except gravity. This is where cosmic ray 28 enters the picture. If certain types of these hypothetical dark matter particles are heavy enough and unstable, they could, in theory, spontaneously decay or collide and annihilate each other. This process would convert their immense mass directly into pure energy, following Einstein's famous equation, E equals mc squared. The result would be a burst of standard model particles, protons, neutrons, electrons fired out with incredibly high energies. In this scenario, a detected ultra-high-energy cosmic ray wouldn't be a particle that was accelerated. It would be the ash from a dark matter fire, a direct product of the invisible universe revealing itself in a single, spectacular moment. The unusual energy signature of this particular ray could be the unique fingerprint of that specific decay process, a calling card from a particle that has never been seen in any laboratory on Earth. The appeal of this theory is that it neatly solves the directional problem. Dark matter isn't concentrated in bright galaxies or clusters alone. It forms an immense, diffuse halo that envelops our entire galaxy and extends far beyond the visible disk of stars. If a cosmic ray is produced by dark matter decay happening within this halo, its path wouldn't point back to a specific bright source in the distant universe. Instead, it would appear to come from nowhere in particular because the source is everywhere and nowhere at once, a vast, invisible cloud that surrounds us. This would explain why the backtracking for cosmic ray 28 led to a complete dead end. The source isn't a point on a map, it's the very space through which the particle traveled. However, this provocative idea is far from settled science and sits at the center of a fierce and ongoing debate. Skeptics argue that it is a solution of last resort, an exotic explanation invoked only because we have failed to find a conventional one. They point out that the properties required for a dark matter particle to decay in this way are highly specific and would need to be finely tuned to match the observed energy of the cosmic ray. Furthermore, if such decays were common enough to produce detectable ultra-high-energy cosmic rays, they should also produce other signals across different wavelengths, like gamma rays or neutrinos, in a predictable pattern. The fact that we haven't consistently seen these correlated signals from the same region of sky makes the dark matter hypothesis a difficult case to prove. The search for a definitive answer is driving a new era of multi-messenger astronomy. Scientists are now cross-referencing the arrival times and directions of ultra-high-energy cosmic rays with data from gamma-ray telescopes, neutrino observatories, and gravitational wave detectors. The goal is to find a smoking gun, a high-energy cosmic ray that arrives simultaneously with a neutrino of a specific energy or a unique flash of gamma rays that can only be explained by a dark matter particle's decay. Until that correlation is found, cosmic ray 28 remains a tantalizing maybe. It is a ghost that could be a sign of the universe's greatest secret, a single data point that carries the weight of either revolutionizing our understanding of the cosmos or simply reminding us that we have much more to learn about the visible universe's own hidden engines. Then we come to a detection that seemed to promise a breakthrough, a moment where two different messengers from the cosmos arrived almost hand in hand, only to deepen the mystery they were meant to solve. This is the story of Cosmic Ray 29 and its elusive partner, a high-energy neutrino. For scientists, this combination is the holy grail of cosmic ray astronomy. A neutrino, often called a ghost particle, is the ultimate cosmic messenger. It has no charge and almost no mass, which means it isn't deflected by magnetic fields. It travels in a perfectly straight line from its source. If an ultra-high-energy cosmic ray is detected at the same time and from the same patch of sky as a high-energy neutrino, it should act like a cosmic zip code, pointing an unwavering finger directly back to the accelerator that created them both. This multi-messenger approach is our best hope for finally solving this decades-old puzzle. The detection itself was a moment of high excitement. The cosmic ray slammed into the atmosphere, and virtually simultaneously, a deep space neutrino observatory, like the ice cube detector buried in the Antarctic ice, recorded a neutrino with a remarkably high energy. For a thrilling moment, it looked like the puzzle was finally solved. Researchers immediately began the complex work of triangulating the paths of both particles, expecting their trajectories to converge on a single, brilliant object in the distant universe, an active galactic nucleus flaring with violence, a supernova remnant, or a colliding galaxy. This was supposed to be the moment where the map was finally filled in, but the universe, it seems, delights in contradiction. When the paths were calculated and extended back through the cosmos, they did not meet. The cosmic ray and the neutrino were not pointing to the same location. In fact, their trajectories were separated by a significant angle, an amount that couldn't be explained by minor errors in measurement or the faintest wisps of interstellar magnetic fields. It was as if two letters, mailed from the same city at the same time and delivered to the same house, had completely different return addresses. This fundamental mismatch created instant and profound confusion, throwing a wrench into what should have been a clean and elegant solution. This disconnect forces a difficult and uncomfortable reassessment of our models. The most straightforward explanation, that both particles were created in the same cataclysmic event and traveled together to Earth, now seems untenable. So what, then, is the link between them? One possibility is that we are seeing the aftermath of a much larger and more complex event. Imagine a single, immense explosion so powerful that it creates multiple shockwaves and acceleration sites spread across a vast region of space. A cosmic ray could be born in one part of this maelstrom, while a neutrino is generated in another, perhaps milliseconds later and light years away. They would be siblings from the same cosmic family, but not twins born in the same instant from the same precise location. Their paths to Earth would be similar but not identical, explaining the directional discrepancy. Another, more radical idea is that the connection is not direct but mediated by something we cannot see. Perhaps the true source is a dense region of dark matter. A dark matter particle could decay, producing both a high-energy neutrino and a burst of other particles that then get further accelerated by a nearby conventional source, like a black hole's jet, into an ultra-high-energy cosmic ray. In this scenario, the two messengers are cousins, related through a common but invisible ancestor, and their slightly different arrival directions reflect their different birth mechanisms within the same general neighborhood. The neutrino link, instead of providing a simple answer, has revealed a layer of complexity we hadn't even considered, suggesting that the universe's particle accelerators may be far more intricate and interconnected than our simplest models allow. And so we arrive at the latest enigma, a messenger that encapsulates every frustration and every thrill of this decades-long quest. Cosmic Ray 30, detected just within the last few years by the most advanced instruments humanity has ever built, arrived with all the hallmarks of a classic mystery. It possessed staggering energy, a trajectory that baffled backtracking algorithms, and a composition that defied easy classification. It was in every way the perfect heir to the Oh My God particle and the Amaterasu event, a stark reminder that despite our technological leaps, the universe is still several steps ahead of us. This newest harbinger didn't resolve the mystery, it deepened it, proving that the problem isn't a lack of data, but a fundamental gap in our understanding of the cosmos's most extreme physics. This particle, more than any other, highlights the frustrating limitations of our current Earth-bound perspective. Our magnificent observatories, like the Pierre-Auger array and the telescope array, are incredible feats of engineering, but they are fundamentally constrained. They can only see the particles that happen to rain down on their specific patch of Earth, and their ability to pinpoint a direction is ultimately blurred by our planet's own magnetic field and the atmosphere itself. It's like trying to understand a magnificent, complex painting by only looking at a few scattered drops of paint that have fallen from it onto the floor below. We're missing the grand picture, the full context from which these incredible energies emerge. Cosmic Ray 30 is the drop of paint that tells us the painting is more beautiful and more bewildering than we imagined, and to see it, we need to change our vantage point entirely. This imperative is what fuels the next great leap in cosmic ray astronomy, taking our search to space. The most ambitious project on the horizon is the POMA mission, the probe of extreme multi-messenger astrophysics. POMA is a visionary concept, a pair of satellites designed to work in tandem, orbiting the Earth and looking down at the atmosphere from above. This shift in perspective is a complete game changer. Instead of waiting for particle showers to reach the ground, these satellites will watch for the faint ultraviolet fluorescence these showers emit as they develop in the thin air dozens of miles above the surface. This technique allows them to see the entire longitudinal development of the shower, providing a vastly more precise measurement of the primary particle's energy and type. But the true revolution of POMA lies in its stereo vision. With two satellites tracking the same shower from slightly different angles, the mission will achieve an unprecedented resolution in determining a cosmic ray's arrival direction. This is the key to finally cracking the case. By drastically reducing the error bars on our backtracking, POMA could transform a fuzzy, degree-wide smudge on the sky into a precise celestial address. Imagine being able to point to a specific galaxy or even a specific region within an active galactic nucleus and say with confidence, "This is where it came from." This precision will allow astronomers to do what they have longed to do for decades: point every other telescope, optical, radio, X-ray, gamma-ray, neutrino at that exact spot simultaneously, creating a true multi-messenger portrait of the cosmic accelerator in action. The potential discoveries are breathtaking. POMA could finally identify the specific mechanisms within black hole jets that boost particles to these incredible energies. It could discover entirely new classes of astrophysical objects hidden in the voids. It might even detect the predicted flux of ultra-high-energy neutrinos, ghostly particles that travel in perfect straight lines, which would act as an unambiguous arrow pointing directly back to their source. Cosmic Ray 30 is the symbol of our current ignorance, but it is also the herald of a new era. It represents the last gasp of the old way of doing things, the final, defiant mystery that old technology cannot solve. The next time a particle of such power arrives, we may not be looking up from the ground confused. We may be looking down from the heavens, finally understanding. To even begin to grasp the enigma of these particles, we must first understand the cosmic engines that theorists believe are capable of such incredible feats. The leading candidate for decades has been a process known as Fermi acceleration, a mechanism so elegant it paints a vivid picture of nature's raw power. Imagine a subatomic particle caught in a turbulent magnetic field surrounding a supernova remnant. This field is not static, it's like a chaotic cosmic pinball machine. The particle bounces back and forth between approaching shockwaves, the vast, expanding walls of gas blasted outward by the exploding star. Each time it crosses the shock front, it gets a tiny kick of energy, much like a surfer gaining speed by paddling into an oncoming wave. Over countless cycles, this process, called diffusive shock acceleration, can gradually boost a proton to tremendous energies. It's a compelling theory, and we see it working beautifully in the remnants of stellar explosions within our own galaxy, producing cosmic rays of impressive but not record-breaking power. The problem arises when we ask this trusted mechanism to account for the absolute monsters we've been discussing. The energy scales involved with particles like the oh my god particle are so far beyond the reach of a standard supernova remnant that it's like comparing a firecracker to a volcanic eruption. The math simply doesn't add up. There's a fundamental size and speed limit to these shocks. A particle can only be accelerated as long as it remains confined within the magnetic trap of the shock region. For the energies we're talking about, the magnetic fields would need to be implausibly strong, and the shock regions impossibly vast to contain a particle long enough for it to reach those levels. It's the cosmic equivalent of trying to accelerate a rocket to interstellar speeds using only a car engine. The principle is sound, but the scale is utterly inadequate for the task at hand. This is why astrophysicists have had to look to the most extreme environments in the universe as potential culprits. The jets from active galactic nuclei, powered by supermassive black holes that are actively feeding, became the next great hope. These are not mere shock waves. They are continuous, relativistic rivers of plasma stretching for millions of light years. Within these jets, a more extreme version of Fermi acceleration could occur, with magnetic reconnection events and multiple nested shock layers providing an almost endless series of energy boosts. The sheer scale is mind-boggling, offering a potential solution. Yet, even here, the models begin to strain. While these engines are certainly powerful enough in principle, the specific details of how they would channel that power into a single proton remain murky. The Centaurus, a misfire, is a perfect example. We found the engine, but its theoretical maximum output still seems to fall short of the particle we actually detected, suggesting our understanding of the engine's mechanics is still incomplete. The most profound challenge, however, comes from the rays that appear to originate from nowhere. A void cannot host a shock wave. Empty space cannot contain the magnetic turbulence required for any known version of Fermi acceleration. This forces us to consider possibilities that sound like they are pulled from the edges of theoretical physics. Perhaps the acceleration isn't happening in a place at all, but is instead a property of the particle's journey. Could immense, large-scale magnetic fields that weave through the cosmic web act as a unified accelerator over tens of millions of light years? Or are we witnessing the decay of primordial relics like super-heavy dark matter particles or cosmic strings, defects in the fabric of space-time left over from the Big Bang? In these scenarios, the particle isn't accelerated in the conventional sense. Its energy is innate, a birthright from a fundamental process that occurred at the beginning of time itself. The failure of our conventional acceleration mechanisms to explain these 30 specific rays isn't a defeat for science. It is a blazing signpost pointing toward physics that operates on a scale and within a realm we are only just beginning to imagine. Catching these cosmic speedsters is a monumental task in itself, requiring ingenuity on a breathtaking scale. Since these particles are too energetic to be detected directly in space, they're so rare that a satellite would have to be the size of a planet to catch a meaningful number. Scientists have devised a clever workaround. They use our own atmosphere as a giant natural particle detector. When an ultra-high-energy cosmic ray slams into an air molecule at the top of the atmosphere, it doesn't just stop, it triggers an avalanche. This collision creates a cascading shower of billions of secondary particles, electrons, muons, photons that spread out and rain down over an area on the ground that can be larger than a city. It's this expansive shower that our observatories are designed to catch. The two titans in this field are the Pierre Auger Observatory in Argentina and the Telescope Array in Utah. Pierre Auger is a behemoth, a network of over 1,600 water tanks spread across 3,000 square kilometers of the Pampa Amarilla, an area nearly the size of Rhode Island. Each tank is filled with pure water and lined with sensitive photomultiplier tubes. When the shower of particles passes through a tank, they travel faster than the speed of light in that water, creating a faint blue glow of Cherenkov radiation that the tubes can detect. By seeing how many tanks are hit and how much light is produced, scientists can piece together the energy and the core of the shower. The telescope array uses a similar method with a mix of plastic scintillator detectors on the ground and fluorescence telescopes that look up to watch the faint ultraviolet light the shower gives off as it develops in the air. This hybrid approach allows for a crucial cross-check of the measurements, but this entire process is filled with inherent uncertainties that directly feed into the mystery. First, there's the energy measurement. We are not measuring the original cosmic ray directly. We are measuring the debris it creates after it has already interacted with the atmosphere. Calculating the primary energy requires running complex computer simulations of how the shower develops, which depends on assumptions about the type of particle that started it. Was it a proton or an ion nucleus? This can introduce an uncertainty in the energy measurement of up to 20 or 30%. That's a significant margin of error when you're dealing with particles that are already defying the laws of physics. Then comes the even trickier part, figuring out where it came from. The secondary particles rain down on the detector array in a specific pattern, and the precise timing of when each detector is hit down to a few billionths of a second allows researchers to triangulate the incoming direction of the original cosmic ray. This sounds straightforward, but there's a major complicating factor: magnetic fields. Our galaxy is filled with a weak but complex web of magnetic fields. As a charged particle like a proton travels through this maze, these fields bend its path, forcing it into a corkscrew-like trajectory. The higher the energy of the particle, the less it is deflected, but for all but the very highest energies, this bending is substantial. When we trace a cosmic ray's path backwards, we have to try to account for this galactic deflection, but our maps of the Milky Way's magnetic field are rudimentary at best. They are based on limited observations and a lot of theoretical modeling. This means the further back we try to trace a particle's path, and the lower its energy, the more the uncertainty in its original direction grows. A particle that seemed to arrive from a seemingly empty void might have actually originated from a brilliant quasar millions of light-years away, its path twisted and bent by magnetic fields we don't fully understand. This directional fuzziness is perhaps the single greatest contributor to the mystery, creating a persistent and frustrating gap between the detection of the particle and the positive identification of its source, leaving us with the haunting question of whether we're staring at nothing or simply misreading the map. This brings us to a fundamental pillar of cosmic ray physics, a theoretical wall that these particles should not be able to breach, yet they consistently do. The Greisen-Zatzeping Kuzmin cutoff, or GZK cutoff for short, isn't just another complex theory. It's a brilliant prediction about the very fabric of our universe and how it governs the flow of energy across unimaginable distances. Proposed independently by 3 physicists in 1966, this concept identifies a cosmic speed limit for protons traveling across the intergalactic void. The reasoning is beautifully elegant. Space is not a perfect vacuum. It's permeated by the cosmic microwave background, the faint, cold afterglow of the Big Bang. This radiation is a sea of low-energy photons, and for a proton traveling at nearly the speed of light, this sea is anything but placid. Think of an ultra-high-energy proton as a supremely powerful race car speeding down a straight, endless highway. The cosmic microwave background is like a constant, gentle rain falling on this highway. For most cars, this rain is just a minor annoyance, but for our proton race car traveling at relativistic velocities, each individual raindrop, each photon, hits with tremendous force. At energies above approximately 50 exa-electron volts, a specific reaction becomes possible. the proton can interact with one of these background photons in a process known as photopian production. In this collision, the proton loses a significant chunk of its energy to create a new particle, a pion. It's the cosmic equivalent of that race car hitting a puddle and hydroplaning, losing control and shedding speed in a violent, unpredictable way. Over millions of light years, these countless tiny collisions should act like a form of relativistic friction, draining the energy from any proton that dares to exceed this theoretical limit long before it could ever hope to reach our detectors on Earth. The GZK cutoff is a predicted cliff in the energy spectrum. Beyond it, the number of detectable cosmic rays should plummet to almost zero. The theory is robust, grounded in well-tested physics, and makes perfect sense. Yet, reality has a different story to tell. Among our collection of 30 unexplained events, a significant number possess energies that soar far above this predicted barrier. The oh my god particle at 320 exa-electronvolts didn't just break the speed limit, it obliterated it. The Amaterasu particle and others like it are not gentle exceptions. They are blatant violations of a rule that the universe itself is supposed to enforce. This presents a paradox of the highest order. We have a sound, theoretically sound prediction that these particles cannot make long intergalactic journeys, and yet here they are, arriving at our doorstep with energy to spare. This forces us into a corner where we must question which part of this elegant equation is wrong. One compelling resolution is that these rule-breaking particles are not, in fact, long-distance travelers. Perhaps they are local, originating from within our own galactic neighborhood. If their source is within the Milky Way or its nearby satellite galaxies, their journey would be short enough that they wouldn't have time to undergo significant energy loss through photopian production. They would be like a race car that only had to drive a few blocks in the rain, arriving at its destination still mostly dry and at full speed. This idea immediately shifts the investigation, turning our gaze inward to hunt for a powerhouse within our own galaxy capable of such immense acceleration. The problem is, as we've seen with other detections, that backtracking often leads to empty space even within the Milky Way, and we lack a confirmed candidate with enough power to serve as such an engine. Our own cosmic backyard seems too quiet to produce such spectacular fireworks. The other, far more thrilling possibility is that our understanding of the particle's journey is incomplete. Maybe the intergalactic magnetic fields that fill the space between galaxies are not the random, weak structures we believe them to be. Could they be organized into colossal, focused tubes or funnels that act as protective corridors? A proton traveling through such a magnetic highway might experience a smoother ride, its path guided in a way that minimizes the number of collisions with the microwave background, allowing it to preserve its energy over a much greater distance than we thought possible. This would mean the universe has built-in express lanes for its most energetic particles, and we are only just becoming aware of their existence. Alternatively, the issue might not be the journey but the traveler itself. The GZK cutoff calculation is specifically for protons. What if these ultra-high-energy cosmic rays are not protons, but the nuclei of heavier elements like iron or oxygen? A heavier nucleus has a different cross-section for interaction. It's a bigger, more robust vehicle on our cosmic highway. While it would still lose energy, the rate of that loss and the energy threshold for significant photopian production are different. A heavy nucleus could, in theory, travel further than a proton while retaining its ultra-high energy, effectively pushing the GZK cutoff to a higher value and allowing these particles to arrive from greater distances. The defiance of the GZK limit isn't just a mystery, it's a critical diagnostic tool. By studying exactly how these particles break the rules, we are given clues about their identity, their origins, and the hidden structures of the universe they passed through on their incredible journey to us. When we search for the source of these enigmatic particles, we turn our telescopes to the most violent and energetic places in the known universe. For decades, astrophysicists have had a short list of prime suspects, colossal engines that seem to possess the raw power needed for such an incredible feat. Yet, as we examine each candidate against the evidence from these 30 specific cosmic rays, every one of them falls short in a crucial way, leaving us with a lineup of likely but ultimately inadequate suspects. At the top of this list are active galactic nuclei, the hearts of distant galaxies where supermassive black holes, weighing millions or even billions of times the mass of our Sun, are actively feeding. As vast amounts of matter spiral inward, a fraction of it is channeled into colossal jets of plasma that shoot out from the poles at nearly the speed of light, stretching for millions of light years into intergalactic space. These jets are natural particle accelerators on a scale we can scarcely imagine, and they seem like the perfect cosmic factory for ultra-high-energy cosmic rays. The magnetic fields within these jets are unimaginably strong, and the shock waves present could theoretically accelerate protons to the energies we observe. However, the problem isn't just power, it's pinpointing the delivery. When we trace the paths of many of our 30 mysterious rays backwards, they simply do not lead us to these brilliant beacons. Even in cases where a path seems to point toward an active galaxy, like the Centaurus a misfire, the energy of the particle often exceeds what our detailed models predict these jets can actually produce. It suggests that while these engines are certainly capable of making cosmic rays, they may not be the sole or even the primary source for the most extreme examples that leave us baffled. Next, we consider the universe's most violent transient explosions, gamma-ray bursts. These events are the most luminous electromagnetic occurrences since the Big Bang itself. In a matter of seconds, a gamma-ray burst can release more energy than our Sun will emit in its entire 10 billion-year lifetime. There are two leading types: long-duration bursts, believed to be the birth cries of black holes formed during the collapse of massive stars, and short-duration bursts, thought to result from the cataclysmic merger of two neutron stars or a neutron star and a black hole. The physics involved is staggeringly violent, involving relativistic shock waves that could, in theory, accelerate particles to the highest energies we record. But here, the central issue is one of timing and persistence. A gamma-ray burst is a singular, fleeting event, over in a flash. If such an event were the source of an ultra-high-energy cosmic ray, we would expect to detect a shower of these particles arriving in a tight cluster during or immediately after the burst. Furthermore, we would expect to see a clear and unambiguous association. A cosmic ray detected on Earth should coincide perfectly with a brilliant gamma-ray flash recorded by our satellites. For our 30 enigmatic rays, this simply hasn't happened. Their arrivals seem random, disconnected from any observed gamma-ray burst, suggesting that if these explosions are contributors, they are not responsible for the specific particles that defy explanation. Another compelling candidate lies in the aftermath of stellar death, supernova remnants and pulsars. Within our own galaxy, we see evidence that the expanding shockwaves from supernova can accelerate particles to very high energies, a process known as diffusive shock acceleration. Pulsars rapidly spinning, magnetized neutron stars can also act as powerful accelerators, with their immense rotating magnetic fields generating enormous voltages. These sources have the advantage of being relatively nearby within our galactic neighborhood, which could explain how a particle might reach us without losing all its energy to the GZK cutoff. This seems to solve the travel problem. However, it utterly fails to solve the power problem. The energies required for particles like the oh my god particle are simply too high. The magnetic confines of a supernova remnant or a pulsar magnetosphere are too small to contain a proton long enough to accelerate it to 320 exa-electron volts. It would be like trying to power a cross-country jet with a car engine. The mechanism is sound, but the scale is off by many orders of magnitude. These galactic engines are powerful, but they are not nearly powerful enough to be the sole origin for the most extreme cosmic rays. This repeated failure of known astrophysical objects forces the profoundly exciting possibility that we are dealing with something entirely new. The rays that point to empty voids, the ones with anomalous compositions, and those that defy the GZK limit, may be our first evidence of physics and phenomena that are not yet in our catalogues. This could include the annihilation or decay of super-heavy dark matter particles, hypothetical relics from the very early universe that could decay and release their immense mass energy as a burst of standard particles. It could involve topological defects in the fabric of spacetime itself, cosmic strings, or other exotic structures predicted by some grand unified theories that could release unimaginable energy as they snap or decay. There is even the possibility of entirely new acceleration mechanisms that we haven't yet conceived, operating in the quiet, dark spaces between galaxies. Each of the 30 unexplained cosmic rays is not just a mystery, it is a potential doorway. While active galaxies, gamma-ray bursts, and stellar remnants remain important pieces of the cosmic ray puzzle, their consistent shortcomings in explaining these specific events tell us that the universe still holds its most powerful secrets close, waiting for us to think beyond the brilliant lights and consider the darkness in between. This multi-pronged approach, known as multi-messenger astronomy, represents our most sophisticated strategy yet for cracking the cosmic ray code. Instead of relying on a single type of signal, it integrates data from completely different cosmic messengers, neutrinos, gamma rays, and gravitational waves alongside the traditional detection of particle showers. Each messenger carries unique information and suffers from different limitations, so by combining their stories, we can triangulate the truth with far greater precision. A neutrino, for instance, is the ultimate truth teller in terms of direction. Because it has no electric charge, it isn't deflected by magnetic fields. It travels in a perfectly straight line from its source. If we can catch a high-energy neutrino that arrived at the same time as an ultra-high-energy cosmic ray, its unwavering path should point directly back to their shared origin, cutting through the magnetic confusion that plagues cosmic ray astronomy. Gamma rays add another powerful layer to the investigation. Many of the suspected accelerators, like active galactic nuclei or gamma-ray bursts, are prodigious producers of high-energy gamma radiation. Detecting a significant flare of gamma rays from a specific galaxy at the same time a cosmic ray arrives would be a colossal piece of circumstantial evidence, strongly linking that event to the particle we detected. Gravitational waves, the ripples in spacetime caused by cataclysmic events like merging black holes or neutron stars, provide a third, independent witness. A cosmic ray detection coinciding with a gravitational wave signal would not only point to a source but would also tell us the type of event that caused it. A monumental breakthrough in understanding the engine behind the acceleration. The potential of this combined approach is breathtaking, and there have been tantalizing glimpses of success. In 2017, the astronomy world was set alight when the IceCube Neutrino Observatory detected a high-energy neutrino, and alert systems automatically directed telescopes around the world to its origin. They found a flaring blazar, a type of active galaxy with a jet pointed directly at Earth, and subsequently found that a lower-energy cosmic ray had also arrived from that general direction around the same time. It was a landmark moment, a proof of concept that multi-messenger astronomy could work. Yet, when we apply this powerful toolkit to our collection of 30 unexplained ultra-high-energy cosmic rays, the mysteries persist. For these specific, most extreme particles, the correlations have not materialized. We have not seen a smoking gun combination of all messengers arriving in unison from a single, identifiable point for any of these events. This continued failure is deeply revealing. It suggests that the sources of these particular cosmic rays may operate in a way that is fundamentally different from the sources we understand. Perhaps they are events so rare and fleeting that we have simply not been watching long enough to catch all the messengers simultaneously. Maybe they produce particles with unimaginable efficiency, but are surprisingly quiet in other wavelengths, failing to emit the bright gamma-ray flares or the powerful gravitational waves we expect from a cataclysm. The most intriguing possibility is that these particles are not being produced in a single, brilliant flash, but are instead the product of a slow, steady process. A dark matter halo decaying over eons, for example, would steadily emit cosmic rays without the accompanying fireworks of a gamma-ray burst or the space-time ripples of a merger. It would be a silent, invisible source, detectable only through the rare particles that happen to travel our way. The fact that even our most advanced, integrated approach has yet to solve these 30 mysteries doesn't mean the method has failed. It means the universe is forcing us to consider even more exotic and unexpected explanations for its most energetic enigmas. But this cosmic backtracking is not as simple as following a straight line on a map. To understand why so many of these 30 cosmic rays point to nothing, we must grapple with one of the most pervasive and invisible forces in the universe: magnetic fields. These fields are the ultimate cosmic pranksters, the unseen hands that reach out and twist the paths of these charged particles, sending our detective work spiraling into confusion. Imagine a proton as a messenger running a straight path to deliver a letter. Now imagine that the entire landscape it runs through is a hall of mirrors with invisible forces constantly pulling and pushing it off course. That is the reality of its journey through the magnetized universe. This deflection happens on two scales, galactic and extragalactic. Our own Milky Way is wrapped in a vast, complex web of magnetic fields. These fields are generated by the churning motion of ionized gas within the galaxy's disk and are thought to be organized into a large-scale structure, though our maps of it are still rudimentary, like early navigational charts of the ocean with vast, unexplored regions. When an ultra-high-energy cosmic ray enters this galactic maze, it begins to corkscrew along these invisible field lines. The amount of bending depends on two things: the strength of the magnetic field and the particle's own energy. A lower energy particle is like a paper boat on a rushing river, tossed and turned by every ripple and current, its original direction becoming completely lost. A higher energy particle, like the ones we're discussing, has more momentum. It's like a massive ocean liner. It still gets pushed off course, but the deflection is smaller and more predictable. Or at least it should be. The problem is that our understanding of these magnetic fields is still in its infancy. We know they are there, but their precise strength and orientation in any given part of the galaxy are largely unknown. This means that when we try to rewind the path of a cosmic ray, we have to run complex computer simulations that apply our best guess model of the galactic magnetic field to calculate the most likely origin. For several of our 30 mysterious rays, this backtracking process, even after accounting for the estimated magnetic deflection, still leads to a blank spot in the sky. The magnetic rebel is a prime example. Despite its immense energy, which should have minimized magnetic bending, its recalculated path led to an unremarkable void within our own galaxy, a place devoid of any known object capable of such acceleration. This leaves us with a chilling possibility. Either our map of the galaxy's magnetic fields is profoundly wrong, or the source is something our telescopes cannot see. The confusion doesn't end at the Milky Way's edge. Beyond our galaxy lies the even more mysterious realm of extragalactic space. The voids between galaxies are not perfect vacuums. They are threaded with faint, large-scale magnetic fields. We know almost nothing about the strength and structure of these fields. Could they be organized into colossal, funnel-like structures that can grab a particle from a distant quasar and bend its path so severely that it appears to originate from the heart of an empty void? This might explain the Amaterasu particle and the twin anomalies that followed. Their trajectories pointed directly into the local void, a region of profound emptiness. Our conventional models suggest that any magnetic fields there should be far too weak to cause such a massive deflection from a true source billions of light years away. But if our models are incorrect, if those intergalactic fields are stronger or more structured than we believe, then we are being completely fooled. The void is not the source. It is merely the exit sign on a cosmic highway that stretches back to a hidden powerhouse we have yet to identify. This magnetic mayhem transforms every cosmic ray detection from a simple clue into a complex cryptographic message. The direction of arrival is not a clear pointer. It is a distorted signal that has been encrypted by the magnetic fields it passed through. Decrypting it requires a key, a perfect understanding of those magnetic environments. Right now, we are trying to break the code without the full cipher. Each ray that points to nothing is not a failure of observation. It is a measurement of our own ignorance about the invisible architecture of the cosmos. They are not just messages about their origins. They are also probes that have sampled the magnetic landscape of their long journey. And they are telling us that our charts of that landscape are still woefully incomplete, filled with unseen currents and invisible walls that redirect the universe's most energetic messengers. The quest to solve these cosmic riddles is driving the most ambitious astronomical projects of our time, moving beyond Earth-bound observatories to a new era of space-based detection. Leading this charge is the proposed POMA mission, a pair of satellites designed to work in concert from orbit. Unlike ground arrays that wait for particle showers to reach the surface, these satellites will peer down at the atmosphere from above, watching for the faint ultraviolet glow these showers emit as they develop dozens of miles up. This perspective is a complete game changer. It allows scientists to see the entire longitudinal development of the cascade, providing a far more precise measurement of the primary particle's energy and, most crucially, its type. But the true revolution lies in stereo vision. With two satellites tracking the same shower from different angles, POMA will achieve an unprecedented resolution in determining a cosmic ray's arrival direction, effectively cutting through the magnetic fog that has plagued our backtracking for decades. This leap in precision could transform a frustrating, degree-wide smudge on the celestial map into a precise cosmic address. Imagine being able to point to a specific galaxy, or even a specific region within the turbulent jet of an active galactic nucleus, and say with absolute confidence, this is the source. Such a definitive identification would instantly catapult our understanding from theoretical speculation into concrete observation. The moment that happens, every other telescope on Earth and in space would swing into action. Optical, radio, X-ray, gamma ray, and neutrino observatories would all train their focus on that single spot, creating the first true multi-messenger portrait of a cosmic accelerator in the very act of firing its unimaginable projectile. We wouldn't just know where it came from, we would see the engine itself, studying its mechanics and dynamics in real time. Among the 30 unexplained rays, the most promising candidate for a first identification might be one like the Centaurus, a misfire. Here we have a known object, a nearby active galaxy that is a prime suspect, yet the particle's energy defies our models of its capabilities. If a future space-based observatory like POMA were to detect another ultra-high-energy particle and trace it with pinpoint accuracy directly to the heart of Centaurus A's jet, it would force a monumental revision of our physics. We would have to accept that our understanding of particle acceleration in these environments is fundamentally flawed, that black hole jets are even more powerful and efficient than we ever dreamed. This would be a profound discovery, but one that fits within an existing framework. We found the workshop, and now we must simply understand how its tools can produce such an unexpectedly powerful product. Alternatively, the first solved case could come from the opposite end of the mystery spectrum, a particle that appears to emanate from a void. If a mission like POMA were to trace one of these enigmatic rays, say a successor to the Amaterasu particle, and its path, even with ultra-high precision, still terminated in the utter emptiness of the local void, the implications would be even more staggering. This would be the most compelling evidence yet for the existence of truly exotic physics or hidden astrophysical phenomena. It would force us to seriously consider the possibility of dark matter annihilations, the decay of primordial relics from the Big Bang, or colossal magnetic structures woven through the cosmic web that we have not yet learned to see. The identification of a source in a void wouldn't just answer a question. It would open a door to a whole new chapter of physics, revealing a universe operating by rules we are only beginning to glimpse. The data from these future missions will do more than just identify sources. It will provide the statistical weight needed to finally validate or refute the most daring theories. By collecting a much larger sample of these rare events with exquisite precision, patterns will emerge. We might discover that all particles above a certain energy consistently point to voids, strongly supporting dark matter decay models. Or we might find they all originate from a specific, rare type of galaxy we previously overlooked. These are the answers that have been just beyond our grasp, waiting for the technology to catch up to our curiosity. The next time a particle of such impossible power arrives, we may not be looking up from the ground, confused and tracing paths through a blurry magnetic maze. We may be looking down from the heavens, finally receiving the universe's message with perfect clarity, ready to understand the magnificent and violent engines that have been calling out to us for millennia. So what are we left with after this journey through 30 of the universe's most confounding messages? We are left with a collection of paradoxes, particles that carry the energy of a well-thrown baseball compressed into a single subatomic speck. Particles that point to vast cosmic voids where nothing known to science should exist. Particles that arrive in pairs, suggesting repeating engines, and particles that travel for billions of years, defying the very physics that says their journey should have been impossible. Each one of these 30 events is a masterclass in cosmic contradiction, a data point that simply should not be, according to the rules we have written for our universe. They are not merely outliers on a graph, they are fundamental challenges to our understanding of reality, forcing us to question the very nature of matter, energy, and the fabric of space-time itself. This relentless assault of anomalies tells us something profound. Our map of the cosmos is still woefully incomplete. We have charted the galaxies and the stars, but we are only just beginning to understand the invisible forces that shape the space between them. The magnetic fields that twist particle paths, the dark matter that may be hiding in plain sight, the possibility of entirely new physics operating at energies we can scarcely replicate, these are the new frontiers. These 30 cosmic rays are the signposts pointing toward that unexplored territory. They prove that the universe is far stranger, far more violent, and far more creative than we ever imagined, operating with a set of tools we have not yet found in our own scientific toolbox. They humble us, reminding us that for all our knowledge, we are still beginners in a cosmos that has been running experiments on a scale we are only beginning to perceive. The story of these particles is far from over. In fact, it is entering its most exciting chapter. The very questions they raise are now driving the next generation of discovery. Missions like POMA, designed to gaze down at our atmosphere from orbit, promise to cut through the magnetic confusion and finally pinpoint the origins of these energetic messengers. Every new detection adds another piece to the puzzle, and with advanced computing and multi-messenger astronomy, we are closer than ever to a breakthrough. The greatest discovery in this field may not be finding the source of one particle, but in realizing that the answer encompasses all of them, a unified theory of cosmic acceleration that explains the voids, the galaxies, and the ancient travelers alike. This is not a mystery that is ending, it is a mystery that is evolving, and we all have a front row seat to the revelation. Your curiosity is the most important tool in this endeavor. Stay engaged with these space mysteries, for the next headline might be the one that changes everything. Follow the work of the great observatories, share these enigmas with others, and never stop asking the big questions. The universe has sent us 30 telegrams written in a code we are still breaking. Let's see what the next one says.